There's a loudspeaker which sends sound waves to an air-water interface. 3 wavefronts are given, and the angle that the wavefronts make with the boundary is given as angle theta. Part I gives us the speed of sound in air as 340 meters per second, and the speed of sound in water as 1,500 meters per second. The question is asking us the maximum angle so that the sound can enter the water. Now, there are two things we have to realize here. You have to realize that the speed of sound in water is given faster than the speed of sound in air, which is what we should expect because this is a sound wave and we learned before that it travels faster in water than in air. So we have the speeds in both mediums, but how do we answer the question? What does it mean the sound can enter the water? This is your clue to think about critical angle. Because if the angle of incidence is equal to the critical angle, remember that the angle of refraction is 90 degrees as measured from the normal. So we're looking for the maximum angle it can approach the surface to enter the water so it doesn't refract at 90 degrees. Geometrically, we need to figure out how this angle falls in Snell's law formula because we know from Snell's law that the ratio of speeds will be equal to the ratio of the sines of angles in the two mediums, but these angles must be measured between the ray and the normal line. So geometrically, you can see that this angle, if you draw the normal line at the point of incidence, this angle will have to be equal to the angle of incidence because this is a 90-degree angle and that is also a 90-degree angle. So say if this is 30 degrees, that's 60 degrees, which makes that 30 degrees. So the angle the question asks is actually our angle of incidence. So to find this maximum angle in air to cause the angle in water to be 90 degrees, we're going to substitute 90 degrees for water, and substituting the values for the speeds gives us that. So theta max is inverse sine of 0.227, which calculates to 13 degrees. The question also instructs us to give our answer to the correct number of significant figures. To decide how many significant figures we have to choose, we look at the given numbers in the question, which are both given to 2 significant figures, so our answer has to be also in 2 significant figures. The second part of the question tells us to draw lines on the diagram to complete wavefronts A and B in water for angles less than theta max. So now we're supposed to complete this diagram in the water with a reasonable alignment of the wavefronts. So we know it's getting faster, which means the angle in the second medium is going to be larger. That could be our ray in the second medium. And to complete wavefront A, to go perpendicular to this new ray, I can do that. And parallel to that, I can draw the same for B. I also want to continue for C. You see that these are in perpendicular alignment with the ray. And you can observe that the wavelength actually is bigger in this medium than in the first medium. Okay, this question gives us an ice cube and a light ray entering the ice cube at an angle of incidence of 46 degrees. The angle of refraction inside the ice cube is given as 33 degrees. Calculate the speed of light inside the ice cube. To do that, we need Snell's law. The ratio of the sine of the angle in air to the sine of the angle in ice should be equal to the speed ratio. We know the speed of light in air is 3 times 10 to the power of 8. This is given in the data booklet in the table of constants. So substitution gives that, rearranging for the speed in ice, we found that to be 2.27 times 10 to the power of 8 meters per second. Part 2 asks us to show that no light emerges from the side AB. That means the only case where light does not emerge from inside an ice cube could be that the angle of incidence is larger than the critical angle. And to show that this is the case, we have to find the angle of incidence on the side AB, and we have to calculate the critical angle for the ice cube using the information we have from part I. So let's complete the diagram to find the angle of incidence on side AB. Draw the normal line. We need to find that angle and show that it is larger than the critical angle. To find that angle, we're going to use this right triangle right here and see that angle of incidence is 90 minus 33, which is 57 degrees. To calculate the critical angle, we will use this formula that we learned before. You remember, please, that you can find this formula in option C section of the formula booklet. We don't know n, but we know the speed in ice and the speed in air. So let's calculate n. This gives 1.32. Substitution in the above would give us inverse sine of 1 over 1.32, and calculation gives 49 degrees. So 57 is larger than 49, which means total internal reflection takes place. Part 3 asks us to sketch on the diagram the subsequent part of the light ray. Since now we know this is going to internally reflect, I show the reflection from side AB, and from the opposite side, I know that's a 33 degrees, which means light will follow the path as it entered. It will get faster, so it will leave the ice cube with 46 degrees to the normal line.